The lung on a chip is a microdevice that has the potential to replace animals for the testing of drugs and toxins. The device, which is lined by human cells, mimics the mechanical and chemical functions of a living, breathing lung. With every breath, air enters the lungs, filling and expanding microscopic air sacs. Oxygen is transferred across lung and capillary cells and into the bloodstream. This is also where aerosol drugs are absorbed and where infections and tumors form in the lung. The lung on a chip is crystal clear, flexible, and about the size of a small computer memory stick. But it contains tiny hollow channels created using microchip fabrication techniques. A porous, flexible membrane separates the two channels at the center of the device. The opposite sides of the membrane are lined by human lung and capillary blood vessel cells. This mimics the arrangement of lung and blood vessel cells in the air sac of the lung. Application of cyclic suction in side channels makes the entire flexible sheet and cells stretch and relax rhythmically, just like our lung cells do when we breathe. In the lung on a chip device, air flows over the top of the human lung cells, and a liquid medium containing human white blood cells flows below the capillary cell layer. To test how well the lung on a chip device replicates the natural responses of living lungs, we introduced bacteria into the air channel to mimic an infection. And we introduced white blood cells to the blood channel. We then saw the white blood cells migrate across the capillary cell layer, through the pores of the central membrane, and into the airspace where they engulfed the bacteria. Here's a video that shows this response, in real time, viewed through the device. The tissue cells are not visible here, but we can see white blood cells flowing freely in the capillary channel of the device, just as they do in blood vessels of a healthy person. But when we infect the air channel by adding bacteria, the immune cells abruptly stick to the surfaces of the capillary cells on the opposite side of the membrane, located directly below the infection site. Here is a magnified view showing a migrating white blood cell making its way through the first capillary cell layer, wriggling through the pentagonal hole in the flexible membrane, and then moving out of focus to the other side. When viewed from the air channel, with all cells visible, you can see a round white blood cell popping up from below. Just like in a real lung infection, the white blood cells, which are now colored red, engulf and kill the green bacterial invaders. We've also had success in mimicking pulmonary edema, a condition in which fluid leaks from the bloodstream into the air sac. To mimic the edema, we introduced interleukin-2 into the blood channel. This is a cancer drug that is known to cause pulmonary edema as a side effect in humans. The dose we added was the same that a typical cancer patient receives. When we added the drug without breathing motions, only a small amount of fluid made its way into the airspace. However, when we repeated the experiment with normal breathing motions, the fluid leakage increased by more than threefold and resulted in complete filling of the air channel over the same time course as observed in human patients. We also saw blood clots form in the fluid-filled airspace, again just as is observed in humans with this life-threatening lung condition. The lung on a chip can also mimic the toxic effects of airborne nanoparticles on the lung. In fact, experiments with the device led to the prediction that breathing increases their absorption into the bloodstream. This has been confirmed in animal studies. Bio-inspired microdevices that can mimic whole human organ function, such as the lung on a chip, could potentially replace animal testing and bring new therapies to patients faster and at lower cost in the future.